basically have two samples with two different insert sizes per one. And the high complexity is basically a time series of 5 of these. Unfortunately, a number of participants pooled all these together because it wasn't quite clear if these were just replicates of the same exact sample or if they were meant to be different samples. So since there's a little bit of confusion, some of the tools pooled these guys together. So whenever you see something that says CAMI high, it doesn't say like sample 1, sample 2, sample 3, sample 4, sample 5, that means it was when they pooled those together. So only some of them pooled them together, so we'll just compare those guys themselves. Okay, we also had all the circular elements, and sometimes their abundances can be 20 times higher than genomes. And so we have two different flavors of ground truth. So relative abundances and organismal identity that's unfiltered means you include those elements. Filtered means you don't include those elements. And so by looking at the unfiltered versus the filtered ground truth will allow you to see which methods actually recovered these sort of circular elements or not. To give away a punchline, none of them really recovered any. Okay, review of the metrics that we're going to be using. So there's a few different metrics, and I know that there's definitely room for more of them to be added in. But for this notation, I'm going to let X star be our predicted bacterial frequencies of a particular taxonomic rank R, and XR be the actual of the ground truth. So the metric that kind of says, do you get your raw abundances correct, is the L1 norm. It's basically just the total error between the prediction and the ground truth. And you want to use L1 norm and not L2 so that you don't have like larger or smaller bins contributing more or less. And then, if you want to figure out if you got your abundances biologically accurate, you use unifrac. And just a quick recap on what unifrac does is it takes your taxonomic tree, so pretend that these are labeled with different rank names, and for sake of not having to get way bogged down in the details, in the CAMI challenge we just assume all the branch lengths are 1. Not a totally realistic assumption, but it's very hard to get branch lengths for the entire NCBI taxonomy tree in such a way that people aren't going to argue with you about it. So unifrac basically takes two samples, like a green sample, let's say that assigned abundances of these 3 nodes, red sample at those 2 nodes, and unifrac tells us the most efficient way to get one of these guys to overlap one of those guys. So even if you didn't get the exact, like this is ground truth and that's reconstruction, if you didn't get it exactly correct, that would give you an error here, but it's close, so it's going to give you a smaller error here. Next, we treated these as a binary classification, so true, positive, false, negative. However, you always worry about a cutoff, like a cutoff value. So in other words, the support of these vectors are going to be all the indices that are above a certain cutoff. When we pick the cutoff to be 0, because it's really rather arbitrary to say, oh, well, anything below, I know 1,000th of a percent is a false positive, so just ignore those. So we just took that cutoff value to be 0. Standard measures of true, positive, false, negative. Sensitivity and precision are sort of the summaries of these guys. So there's our precision and there's our sensitivity. So difficulty with visualizing this stuff, so I don't have to impress upon you guys how hard it is to try to summarize all this information together, because think about it, we have 3 different classes of samples with a varying number of samples per class. 1 low sample, thank goodness. 2 samples of the medium with 2 different insert sizes, 5 of these guys, and then we have filtered and unfiltered, and then we have 7 different error metrics and 12 methods, and some of those methods have up to 7 versions per method, so a high dimensional manifold to try to visualize. Okay, so let's actually try to do that then, and actually visualize these things. So the very first question that I wanted to answer is, what about versions? How important does version implementation make for these various methods? And similarly to what we've seen earlier today, holds true here as well. So we had different anonymous names with multiple versions, like these guys right here, and as well as some of these approaches, these profiling approaches, were implemented by CAMI personnel, and then other ones were different versions actually implemented by the participant. So the participant might have tweaked a few different parameters and made a new resubmission. If it has an S in the name, that means that's what happened. if we really wanted this one tool to be implemented and nobody volunteered to do it, so CAMI personnel had to do it, it has a D in it to mean it was implemented by CAMI, default parameters. Okay, so parameter set by participant, that's the S, sometimes had a little effect. So look at all these S1s through S6s, and you can see that for the low sample across taxonomic ranks, the L1 norm really didn't change. Similarly over here, L1 norm at the low sample over taxonomic ranks, these two, atom S1, S2, don't change. And in fact, atom D, which was implemented by CAMI personnel, was completely identical to atom S2 right here, because that participant submitted it with default parameters. Sometimes, however, the effect is large. So you might imagine if you change the norm with the high sample across taxonomic ranks, the sensitivity, it varies quite a bit up here at the higher taxonomic ranks. As well as over here, this is one of the most stark ones. Once again, sensitivity. You have a highly sensitive parameter settings, very low sensitive parameter settings. The same thing was shown whenever it was implemented by participant versus CAMI. Sometimes little effect, no difference between those two guys for false positives across taxonomic ranks. High complexity sample. Right here, notice this one says just CAMI high. This is the pooled one. So all 5 ones thrown together in one big file and then profiled. And sometimes it had a large effect. So here's one that was implemented by CAMI participant or personnel. This one was by participant. And so you could see that the designer of this tool did not trust it past species, because they just cut off all the species, said, I'm not going to leave anything past species. And so that's why it has 0 false positives here. Whereas if you just leave everything default, then you get this massive false positive guy up there. So that can be first take-home messages. Parameters matter, which is one of the cool things about having these tools submitted by the actual tool designers, is because somebody might not know this. They shouldn't really trust it past the species. Okay, second versus taxonomic rank. So similarly to the binning tools, kind of which taxonomic rank do things start to really decay? And so we have these sorts of plots. So how does this performance change over taxonomic rank? Let me explain this real quick. So over here will always be your error metric. And then we have all the different methods along over here, sorted alphabetically. And then we have phylum, class, order, family, genus, species. And way up here is which sample that you're looking at. So this is the low complexity sample. So this is L1 norm, lower is better. And so you can see that just generally overall, the area right here is getting larger the farther you go down, which makes sense. It's more difficult to do these lower taxonomic ranks. But if you go down even to the genus level, getting your abundances correct was pretty uniformly difficult for every single one of the methods at the genus level. One thing to note, there was a little bit of differences between how strains were reported by participants and how they were represented in the ground truth by CAMI. So because of that difference in representation, strains aren't shown at all, because we really couldn't compare them. So that's why we just got out of species. But you can kind of imagine what it would be like if you're doing this poorly at the genus level. Then you're not going to do better at a lower level. These little notches right here, due to the fact that these two methods don't give any species level predictions, and because of that, that means that your L1 norm is going to be equal to 1, because L1 norm at max is 2, at minimum it's 0, and if one of the vectors is all zeros, the other vector sums to 1, then of course that difference is going to be 1. So this just indicates that those two methods didn't make any assignments there. Similarly, changing your error metric, for instance, to precision, you can see the same general effect, that the red area gets smaller as you go down. Here, however, there's a couple of standouts. For instance, this atom S1, but primarily Hank D right here, stays precise pretty much no matter what the taxonomic rank is. And then also due to the jaggedness of this plot, you can see that precision varies pretty wildly across these different methods. And this is for one of the medium samples. Once again, changing our sample and our metric again. Now we're looking at sensitivity on the high one. And here again, you can see the area decay. And so down here at species level, there's like almost no sensitivity with a tiny little bit by one of these methods right here. Whereas pretty much at the genus level is when you want to start getting suspicious. However, at the family and above level, doing pretty well. A little bit less jagged than these guys, so the amount of variability of sensitivity across methods is less. Okay, I'm going to see effective filtering. How does filtering affect performance? Well, for some of the metrics, it doesn't at all, like true positives. That's not going to be affected by whether you included the circular elements in your ground truth or not.
What is filtered? What was filtered?
Filtered means, did our ground truth include the circular elements, or did they not?
No.
Yep. Yeah, so where you can see this is, for instance, like at the super kingdom level. So here is the CAMI low sample, including the circular elements in the ground truth. L1 norm, every method does uniformly bad. However, when you filter it, then the L1 norm, this is lower is better, everybody uniformly improves. Now, the reason why this filtered versus unfiltered makes such a big difference for the profilers is because, remember, a profiler just returns a list of identities and relative abundances. And pretty much none of these tools adjust for genome size at all. So even if you had a bunch of plasmids that are very small, but if their abundance is 20 times everything else, then in that list, it's going to be dominated by those. And that's why you see this, massive poor performance. That's like the same. Everybody does terrible there. Similarly for for unifrac, once again, it's a little bit less pronounced here. But you can see that each one of these decreases when we go from everything to filtered. The good thing is that the relative performance of these guys are pretty much preserved. Okay, concentrating on a few other metrics, like what about precision versus sensitivity? So let's do these sorts of plots. We've seen one similar to this here, however, I have sensitivity on this axis, precision on that axis. I'm going to have a taxonomic rank up here. So if you have a method right here, it's performing perfect with respect to these two metrics if it ends up here. If it's up over here, it's more precise than sensitive. If it's down over here, it's more sensitive than precise. We can take a look at these. Oh, there we go. Medium sample. Here we go. So the effect of taxonomic rank you can see here as well, because everything at there are a number of methods over here at the phylum level, and as you march your way down, you can see everything. You just move down to the lower left-hand corner. And you start to see a few different things start to come out. For instance, this Adam over here, you see Hank, and Adam, Hank, Caesar, Hank, Adam, Hank. Hank and Adam, we'll see that pattern overall. They prefer precision over sensitivity. And then you have some other methods like down here, Gustav, 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 which is preferring sensitivity over precision. Now, this right here is the second sample of the medium guy. So you can see that if we flip back and forth, they don't change a whole lot. They kind of wiggle around a bit. But again, you see the Hank, Caesar, Adam, Hank, Adam, Hank, Adam, Gustav, 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 like that all the way down. So same patterns between the two of them. When you go to the high, those same patterns remain at the order, family, and genus level. All of a sudden, you then see this little Frank pop up over here. But then again, at the high sample, down at the species level, precision and sensitivity, every single method is doing uniformly poorly. One thing to note for these down here You might say, well, that, 0.2 versus 0.4, how much worse is that really for precision? So let's just drill down and take a look at this particular method and see what does it mean when precision right here is at 0.2. So this is what it looks like for those star plots that I had. Here's Gustav right there. That's right around 0.2 for the precision. To really drive home what that means, let's go ahead and take a look at taxonomic rank. This right here is ground positive, or ground truth positives. And this is a plot of the false positives. So you can see how, let's see here. There were only 200 different genera in the high sample, and Gustav predicted that there were about 1,100 at just the genus level. So this little bit of precision, this little dip right here, can translate to a large difference in false positives. So just be aware of those kinds of things. Yeah?
So I'm not sure if I understand this. So ground truth positives, what is it exactly?
So look in your ground truth, count how many different genera there are.
Why are there false positives?
No. So I'm showing two different things on here. Unfortunately, I couldn't get two different legends. But yes, green is ground truth positives.
Oh, okay. And you have
This
to compare the
is false
blue
positives.
to the green one, basically.
Yeah, I should have moved to this, to the label right there. Yep. Yeah, so I wanted to show the relative difference. Yeah. Okay, so now let's go on to my favorite part. You might think that we're almost finished because we're in the last one right here, but that's where I stuck all the really interesting plots. Okay, so I want to look at relative performance. So let me explain these plots real quick. So once again, for a particular sample doesn't matter for this one because I'm just explaining what this is. You have your taxonomic rank up here. Once again, you have your methods, and we have all 5 of our error metrics right here. And then everything is normalized, so the maximum value equals 1, so it's normalized by its range. Again, for instance, unifrac at maximum is 16, so we can just divide through by 16, or the maximum that we actually observed in the data, etc. So that if, for a particular line color, it's lowest, that means it has the least unifrac error at the genre level for whatever sample. And, like for the red right here, that's the largest out of all these guys, so that means this one is the most sensitive. Green right here, L1 error, has least L1 error. Black by far most precise. Whoop. And this one, most false positives. So,
Shouldn't you turn the last one around, the one with the least false positives?
I debated about this, but from my own interpretation, when I saw high false positive, I really wanted that to mean high false positives. Yep. So for false positives, L1 error and unifrac error, larger is worse. For sensitivity and precision, higher is better. So just think, sensitivity and precision, you want those bigger. So you want the red line higher, the black line higher, all other lines you want smaller. Yep.
So Gustav asked, even though he has the questionable honor of being one of the most false positives, he also seems kind of sensitive, right? So it's one of the more sensitive.
Absolutely, yes. And you see that playoff between false positive and sensitivity a little bit later on. So for instance, right here, this guy, it's most sensitive, and yeah, look, the false positive rate is the tied for the second highest. Yep. Okay, so let's go ahead and look at these. So this is for the low, and the low sample is the one that had the most submissions. There was only a single file in there, so everybody knew how to run it and all that kind of stuff. In phylum, class, order, family, genus, species, once again, those same sort of observations that we saw beforehand, like notice the black lines right here, precision, higher is better, and you can see the black line slowly disappear. Once again, this Hank right here, it's pretty awesome precision at every single different level. Frank is tied, and then it starts to drop off at the lower taxonomic ranks. And you can make a few observations about these guys, like this one has high sensitivity, but a high false positive rate. And this one has consistently good abundances, so the lowest L1 norm and unifrac, and consistent precision and sensitivity, et cetera, et cetera. You can stare at these for hours. We won't. But for the pooled sample, let's go, hello. There we go. There we go. So this guy, I'm going to go ahead and use my keyboard because battery might be dying. This is for the filtered, right? This right here is for all. So filtered, all, filtered, all. And if you flip back and forth, you can see what are the things that are changing: unifrac, error, and L1, which makes sense. Because pretty much nobody got the identity of the circular elements correct. So just the L1 norm and the unifrac are the things that are changing. Really curiously, I'd spent a lot of time trying to figure this out with matplotlib. Notice this guy right here? How that moves? That says the sensitivity is changing, going from filter to all. It doesn't. Which is really odd because this particular method, this Brian S5, didn't predict any circular elements at all. No plasmids, no viruses, no nothing. So there's no way that its sensitivity could change going from one to the other. So I don't know what that is. It might be because these are spline interpolations of points. So this might be an artifact of that. Okay, moving on. Medium S1, sample 1, filtered across all of these guys. The same sort of general things that you're seeing hold true. Gustav again has most false positives, but also has one of the highest sensitivities. Hank is again the most precise, et cetera, et cetera, et cetera. So you can make those similar observations. If you pooled everything together, so take all 4 of the medium samples and pool them together. So Adam, Brian, and Caesar were 3 participants that did this. And this is the sort of thing that you can get. And you can see that the precision is, or Adam is a precise guy, which Adam was precise up here as well. So that's no surprise, etc. Caesar again down here, if you notice, has high sensitivity, but unfortunately the unifrac error and L1 norm are the worst. It's getting the identity correct and it's getting the relative abundances incorrect, basically. And you can see that over here as well. There we go. There we go, right there. And you can see this. Okay. Yep, there we go. This is annoying. Organisms right, abundance is wrong. Okay. High complexity sample. Squiggliness of all these lines communicates the wild differences of performance between the different metrics and across the different methods. So for instance, if you want to look at the number of false positives, notice that some of these have very high, some of these have extremely low, some of these have medium, and so it's just all over the place. If you want to look at precision, some of them are extremely high, some of them are lower, some of them are medium. So it varies quite a bit. However, some of the general observations that we made, there are precise methods, there are sensitive methods, and there are sensitive methods with less false positive rates hold true. For instance, notice Hank wins out on precision at every rank again. Okay, more observations. Pull them together, same thing. You got the sensitive ones, et cetera, et cetera. This looks almost identical to when you pull the medium ones. So we can go ahead and just skip that. And then, after I spent a long time staring at all these things, I decided, this is great and this is informative if you're really motivated and really want to dig down into all the little nitty-gritty details. But what happens when people continue to submit methods and you get a lot more methods across here and more error metrics and things like that? How do you automate the conclusions? Because we've stared at this long enough to sort of get a general idea of, Hank is the most precise and things along those lines, but how do we automate those conclusions? So to be able to do that, I thought let's go ahead and use rankings. So let me explain what I'm doing right here. So for a particular metric, like true positives, and a particular sample, these are the taxonomic ranks right here, and they're ranked. Better performance is on top, worse performance is on bottom. And so you have rankings of these guys. And then I want to figure out, notice that each one of these methods, the color remains the same, so you can kind of see how across taxonomic ranks it performs. Like Gustav is doing great until you get to species level, and then it just drops off like that. So let's go ahead and look at the sum of the rankings over taxonomic ranks. So what do I mean by that? Kirk is first, so it gets a score of 0 here, score of 0, score of 0, 0, 0, 0, 0 plus 0 plus 0 plus 0, 0. If you look at Gustav right here, it's 0, 1, 2 is its score, 0, 1, 0, 1, 0, 1, 1, and 18. So you get a score of 25 right here. So it's sort of like a summary guy, a summary metric of the performance. And you can see also the relative proportions between these guys. Say Kirk, for this sample, for this metric, kind of won out pretty solidly because at every taxonomic rank it was the best. Gustav was the second best, not as good, but Gustav and Isaac were pretty similar. And if you find Isaac, right here, Isaac, 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 like that, they kind of switched places over here, and then it does a whole lot better at the species level. So it's kind of a way that you can do a summary. And I wanted to see if this sort of summary would allow us to get the same sorts of conclusions that we did by staring at those more complicated plots. So what you can do is you can go and look at all the different metrics across all the different samples and get all these guys together and then do that for true positive sensitivity, and then, oh look, nothing changes when you do the two of those. Well, of course, because sensitivity is just normalized, and so when I'm doing rankings, it's not going to change. Okay, whatever. Precision, et cetera, et cetera, et cetera. And then you can put all these guys together and make the conclusion that there are no clear winners. So if we look at all the methods that have results for all three data sets, which unfortunately there weren't, we get the following. So we sum up across all the different samples, and we get sensitivity, Kirk wins out. These are the top three, basically. Precision, Hank wins out. Hank and Adam are pretty comparable and a lot better than Frank. Top three of false positives. Now here, higher is still worse, right? Because I'm ranking these guys. Closer to the top, you get fewer penalties. So here are false positives. Adam and Hank win out and are a lot better than Frank. Hey, look, that was the same thing that you got for precision. So we can at least conclude that these methods are precise with low false positives. That makes intuitive sense. You get a trade-off between false positive precision versus sensitivity, because notice none of these methods show up over here. Then we wanted abundances, like L1, norm, and unifrac. Ed, Brian, Isaac, Donald, Ed, Gustav. Ed shows up in both of these right here. Ed does a really good job of getting relative abundances. None of these show up anywhere over here. But all hope is not lost, because basically what this says is that you have sensitive methods, you have precise methods with low false positives, then you have methods that get the relative abundances correct. So depending on what you want, pick from either this class, or that class. That's pretty much what we saw earlier. Hank was the most precise, followed by Adam. Sensitive, Gustav was definite, but it had terrible false positives. Ed had a really good L1 norm. So hey, look at that. These summary statistics gave us the same conclusion by looking at those star charts, and they're automated. So you can do this when you add more of them in there, as well as if you wanted to add weights for different taxonomic ranks, etc.
Were those submissions that had submissions with several different parameters measured differently, or were they averaged out?
They did measure differently. So for instance, this is Adam S1, not Adam S2. Yep. Yeah, great question.
If no biologist looks at this and sees, oh, this one is a really precise one, but in the
yes, with those parameter settings, yeah.
But the default is bad and the specific ones are better.
Yeah.
If he uses the wrong parameters, he uses the wrong one.
Absolutely, absolutely. Which is great. Why these names will be attached to identifiers to the Docker, so they know pull this Docker. Yep.
This is across all the data sets, right?
Yep, across all data sets, all ranks.
So is there a difference for the different data sets?
So if we wanted to spend time, we could go and look at like false positives across low, medium, high, and you can see things like Hank, 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 Caesar. Oh, no Caesar. Adam, Adam, Adam.
Okay.
So some of them are, some of them aren't. You can go and see, you know, where Adam shows up across all these things, or maybe, oh look, Gustav is just uniformly the highest false positives. So worst performance with respect to false positives across, no matter what the complexity is.
So would you weight this by
Absolutely.
the novelty?
Novelty?
Right? Because it might be, hold on.
So you could weight anything that you wanted here. The weights across which rank you're more concerned about, weights across which complexity you're more concerned about, weight whether you want, you know, top half or bottom half performance, etc. But I don't know about novelty.
I'm just wondering if some tools perform better for, well, I don't know, new filer compared to others. Which only
Yeah, that's one thing that I did not look at, because I don't think I readily had access to which one were the novel ones when I made these. But yeah, that would definitely be something interesting to look at. Which ones are good at finding the new stuff. Okay. Binning versus profiling. So this was added just this morning, like right before walking over here, so it's not super complete. But anyways, you can use a taxonomic binner to create a taxonomic profile. And unfortunately, there is confusion in the general community about binning versus profiling, because there are some binners that are also treated like profilers, and there are profilers that are treated like binners, and there's some that are only binners and some that are only profilers. So to try to keep this clear in your head, whenever you think taxonomic binning, think you're working with contigs, or at least somewhat assembled data, and you want to bin those things. Profiling, you're working with raw reads. So the binners, that same algorithm can work on raw reads. Some of them don't. And so I wanted to see the relationship between the two of these guys. So for instance, some of the profiling methods don't assign taxonomy to reads, any of the reads. They just literally return to you a list of identity of organisms and relative abundances. So you have none of the reads in there assigned at all. That could not be used as a binner. So, that distinction at all clear between the two of them? So you often see plots like this, which was actually a really nice paper last year, a large-scale comparison of metagenomic methods. And they have individual samples, and they take just the reads. And then they use all these methods on just the reads. Kraken can do read assignment and contig assignment. So it's a binner and a profiler. And then you have other methods like, this was meant to bin contigs, right? They're using it to assign reads, individual short reads. So I think that's why you can see differences in, well, you might be using it on the wrong kind of data, or, you know, there are profilers and there are binners thrown into here. So let's go ahead and see. If you did use a taxonomic binner, the way that it was meant to be used on contigs, and from that derived a profile, how does that compare to as if you used a profiler just on the raw reads? And that's this next plot. We're going to use bin coverage as a proxy for relative abundance, sum it all up. It's not a completely fair comparison because the taxonomic binners use the gold standard contigs, whereas the profilers use the raw reads. Okay, so now these are the same in order, and then I've just stuck in the top right here all the binners. I have no idea why this weird wedge was there, but I didn't have time to look at it. Low sample right here, L1 norm. So L1 norm means lower is better. And you can see that, for instance, modest Babbage is not doing the world's greatest for the L1 norm. Once again, at the genus level, everybody is uniformly doing poorly, but then some of them, like, oh, look, a different parameter setting, modest Babbage 5, does much better at the L1 norm. Not better than the best of the, evil yellow, where was that? Yeah, like, at the order level, Ed does better. Frank does worse. Modest Babbage is somewhere in the middle. So, it's kind of somewhere in the middle for this sample, for this error metric. To go to a different error metric, I was only given the low complexity ones, so that's the only sample we get to look at. So for sensitivity, once again, parameters matter. Notice the big dip, modest Babbage 5 and 6, those two different settings. And once again, let's take one like this right here, modest Babbage 5. Not the best at sensitive at the class level, and it's not the worst at the class level. So it's somewhere in the middle there. Once again, that same thing else that you observed with below the family level, they do poorly. You see the same thing. Notice how big these guys are, and then all of a sudden, phew,
Yeah.
they jump way down. Yep.
That's nice that this idea like leads to some sensible results.
Yeah. I have it on a couple slides now, so I'll save that comment for a minute. And then same thing with precision. Actually, precision, these are really precise. More so, notice how high up they are. So Hank is again the most precise. Once again, I colored the wrong triangle, but whatever. Hank is the most precise, but then some of these binners are pretty good at their precision. So conclusion, it's not a fantastic improvement and it's not terribly worse. So it's kind of middle of the roadish. They have good family level or above performance and precision. What I'd really like to do is run the profiling tools on the gold standard contigs, because I bet you dollars to donuts that they will just blow all the results out of the park. Because a lot of these tools, if they have longer contigs, they're going to do a lot greater. And if you use the gold standard ones, whew, that'll be even great. So I think that'd be something really interesting to do. Okay, conclusions. Yay, I have 3 minutes, I can do this. Okay, genus and below is still difficult. Genus level below, L1 norm, larger is worse. They're all uniformly bad. Larger is better. Some methods have higher precision, like these guys right here, but pretty much uniformly genus level and below. It's still difficult, even though you have all these methods that talk about strain level quantification and things like that. It's still difficult when you have very realistic data sets, and also for other norms like sensitivity. Wildly different behavior of methods. Look how squiggly all these lines are. So choice of method, very important. Parameters matter, like Caesar. Look at one of the smallest false positives, change the parameter, one of the worst false positives. But we all knew parameters matter. There are sensitive methods. There are precise low false positive methods, and there are methods that get abundances correct. So there are 3 main categories of methods, and there is no method that spans more than one category. So depending on what you're interested in, you're going to have to pick one of these guys. And we saw that with all these rankings right here. None of these show up over here, show up over here. Okay, a couple final thoughts. Visualization is difficult. We've seen a lot of these guys. I did not show any of the plots that Stefan Jansen worked so hard on, like these guys right here. These contain a whole lot of information, and you can see, for instance, the performance for a different metric across all different ranks, and you can see all the ranks right here are labeled, and so you can try to see these sort of global patterns and behaviors here as well. So if anybody has any ideas about how to better visualize these things, I'm all ears. Final thought, dynamic choice of method based on user preferences I think would be a great end goal of CAMI, which basically lets you take sort of a weighted average over complexity or metric or rank and it has this nice little user interface online, so a scientist can go and say, you know what, I really prefer sensitive methods over precise methods and things like that, and they can wiggle around the sliders and they can see which method is better. So it would end up looking like something like this. I think what would be great is so you can have, oh, what kind of complexity? Do you want to perform better on low, medium, or high complexity? You can say, you know what, I really don't care about low complexity because I'm doing soil samples or something like that. So I'm going to go ahead and drag this thing all the way down. You can see the methods change and say, I really care about getting high true positives, and I don't care about getting my abundances correct, and I don't really care about false positives. And they say, well, you know what, you can pick from these methods right here. These are best. And don't pick any of those methods. And then suddenly you say, you know what, no, actually, I don't care so much about getting true positives correct. I don't want to get something there that's not actually there. And then you can see the methods, the rankings switch all the way around. Oh, then you want one of these methods. And that would be really cool if you could integrate this on top of the framework. So basically scientists and users wouldn't have to think. They can go and say, oh, for my particular purpose, pathogen detection, well, maybe in this instance, I don't want to accidentally detect one that's not there. Maybe you really want to detect it if it is there, and you just slide the parameters around, pick your method, and go. So, but anyways, I am now exactly on time. Perfect. Thank you. Any questions?
Yeah, that was really cool. I like those plots, but I also really like the ranking idea because I was starting to get really confused. So that was really nice and informative.
Yeah.
I wonder, you said when you wanted to run the profilers on the context, how would you evaluate that then in the following? And don't they take like week counts to come up with the profile estimates?
No, so the outputs of all the profilers are identical. You know, a list of organisms and relative abundances. How they go about getting that is different. So for instance, like the marker-based techniques or CAMI-based techniques or machine learning techniques. So it would just be interesting to see maybe which one of the techniques does better on that sort of paradigm.
So okay, so it's okay to use the context and then you
Yep.
just use a standard tool and see.
Yep.
Okay, yeah, sure. That sounds like you're probably right that using the gold standard context does give you a substantial advantage.
Improvement. Yep. Which would then sort of drive the point home that I think everybody knows, but maybe not, that profiling is a lot easier than binning. Because binning, you got to get individual contigs correct. In profiling, you don't really care about getting the labels correct on the individual sequences. You just want to know which organism's there and what in relative abundance, which is an easier to answer question. So since we ran all the binners on the gold standard contigs, if we ran all the profilers and the profile results are a lot better, it'll make that point.
Is that possible in the framework to run the profilers on the gold standard context?
If you have the contigs in a FOSTA file, then yep, you would just have to plug it in as input.
I think the reads were ASCII format and the config parser format. So we
Sure.
convert and
Perfect. Cool.
Stefan wants me to say that the versions are different parameter settings.
Yes. Yeah, the S's, yeah, that's way back there, but the S's being the different parameter settings, and the D's being implemented by CAMI personnel. At least that's what the documentation on the on the GitHub website said. So I'm just believing that. Yeah.
I was wondering, so the results at the beginning you showed some measure was really bad for the unfiltered data sets. So what are the abundance estimates, right?
Yeah.
So that's kind of scary if you think about that. There probably are plasmids in real data sets.
Oh yeah.
How are was there results for the other measures on the non-person?
So the binary classification ones don't change.
Okay.
Yep. So only the L1 and the unifrac really change.
Okay.
Yep. And it was kind of interesting because, so I have a couple horses in this race, and I could have easily added plasmids into it, and I had just not. So when I realized, I was just like, of course, I should just go throw it back into the training data set, because that would be very straightforward to do. But
Right. So you
yeah.
think, I'm not really following, so you think that if you added database plasmids, you would get higher, you would identify more of the plasmids from the database?
Potentially, if there were any plasmids included in here that were in existent databases, then they may have been picked up, unless all the plasmids were novel in this thing. Oh, then it might be more difficult, and that would be a more interesting problem. Yeah.
Would explain why the taxonomic classifiers were though poorly on them.
Yeah. Yeah.
And I mean seriously poorly.
Yes. Exactly. Yeah.
Yeah, they're very different, all of them, and they're very new.
Okay. Okay. Cool. So then I think that would be even more interesting is, train these methods just on databases of known plasmids and see if they can at all pick out any sort of
Well, I mean,
similarity.
there should be some plasmids also in the 600 genome, right? We don't know that there's no plasmids in those plasmids just because they haven't
Yeah.
been classified.
Good point. Good point.
Did you throw out in your initial analysis in the assembly? It was not very clear.
For sure, I know.
Yeah, you can't know.
Yeah, we could have looked at the coverages. No, we didn't.
One point about using binners as profilers is they're kind of, there's different ways how to do it, I guess, and this, like counting read amounts or coverage or something is probably the simplest way to do it.
Yep.
But it uses the assumption that the binner does have equal recall on all the taxonomic classes, which I think it's violated right away by the fact that it does better for novel, for known genera than for novel genera.
Yep.
So the recall would be several times fold higher.
Yep.
And then that's basically your screw in the abundance as well.
Yeah. Yeah. Exactly.
So,
Which is how some of these methods do it. Like some of the Kamer-based, like Clark or Kraken. That's how to do it.
Like the Lindgren study that you showed.
Yeah.
They also did it like this.
Mm-hmm.
And that's the natural way.
Yeah.
But maybe it's also another incentive to think about it, how to do it better.
Yeah. Absolutely. Yep.
There's one more comment by Stefan. He says he tried some profilers on the context, but they were very slow since some of them are using glass.
Oh.
Or other things to see homology to marker genes, so not every profiler might run. But I guess
Sure.
for a subset that can. it's
Yeah. And that would be good information to know.
there.
Yeah.
Okay.
Cool.
Well, I really like that, so thank you again.
Yeah.